Welcome to this the fundamentals of transport processes. This is lecture number 15 and we are well on our way to solving problems in unidirectional flows. We had looked in series at a series of problems of increasing complexity. The first few were just flow transport between two flat plates, where the temperature, the concentration or the velocity was at two different values between the two plates, and so there was a transfer of momentum, energy or concentration from the region of higher velocity, temperature or concentration to a lower value. Okay. And then we were looking at some problems where there is a source or sink within the flow. In this case, there is momentum generated due to forces acting on the fluid itself. Alternatively, there could be a source of mass due to a reaction taking place within the fluid, or a source of heat due to various reasons. One could be because of reactions, exothermic or endothermic, resulting in an increase or decrease in temperature. There could also be phase transformations, which result in a release of latent heat. And I had also briefly told you that there could be viscous heating due to the shear stress in the fluid itself. So, in this series of problems where there is a source or sink of mass, momentum or energy within the flow, the first situation we had considered was a body force, a gravitational force acting on a fluid that is flowing down an inclined plane. Okay. So, the problem we considered was the flow down an inclined plane, and there is a gravitational force acting on every element of fluid within the flow. That gravitational force has a component along the flow direction. Okay. This component is of course, if I resolve it into components along and perpendicular, I will get a component both along and perpendicular to the flow direction. The component of the gravitational force along the flow direction is what results in the fluid flow, and that exerts a force within the fluid itself. Okay. And therefore, we have an equation with an inhomogeneous term here. This is an inhomogeneous term which is generating the fluid flow within the due to the force exerted on each volume element of fluid within the flow. So, this is like a source of momentum, and from that we had calculated what was the velocity field due to that. Okay. At steady state, we get the solution quite easily. The important point is we have to impose a zero shear stress condition at the surface. If the surface is between liquid and air, then the viscosity of air is much smaller than the viscosity of liquid. Due to that, the air cannot exert a shear stress on the liquid, and due to that we have to ensure that the shear stress at the surface is equal to 0. And on that basis, we had got this velocity profile, okay, for the flow. Now, another case where there is a force exerted on every volume element of fluid is the pressure driven flow in a channel. Pressure driven flows in channels and pipes are widely encountered. For example, if you want to pump fluid to an overhead tank, there is a pressure gradient that is generated which results in the pumping of fluid to that tank. Of course, that pressure difference has to account for the potential energy of lifting the water all the way to the tank, but also for the friction losses, okay, due to the flow in the pipe. Okay. So, because of that, you will have a pressure gradient which exerts a force on the fluid, and we will look at how to analyze that situation in two respects. One is the flow itself, the flow profile itself, and the second is the viscous heat generated due to the velocity profile. Okay. So, this is a pressure driven flow in a channel. Okay. This channel is in between two flat plates. Okay. So, let us draw the configuration here. You have two plates, one is at z is equal to 0, the other is that z is equal to h. Okay. And these are solid plates. We will assume that they are of infinite extent into the board. This is the x coordinate, this is the z coordinate. And then we have to find out what is the velocity profile within this channel. Okay. Now, obviously, this flow is being generated because there is a difference in the pressure between the inlet and the outlet. Okay. There is a difference in the pressure between the inlet and the outlet, and that is what is generating a velocity profile. Okay. So, the pressure at each and every cross section in the x direction is not a constant. The pressure is steadily decreasing as you go downstream. Okay. So, how do we do the momentum balance? We use a shell balance once again. Okay. Of thickness delta x, delta y, delta z. Okay. And the balance equation is the same. The rate of change of momentum is equal to the sum of forces. Okay. Previously, I had separated out forces into two types. One was body forces and the other was surface forces. In this particular case, for simplicity, we will assume that there are no gravitational forces exerted on the fluid. Okay. So, we will neglect body forces for the time being and consider only surface forces. Okay. The rate of change of momentum within this differential volume is given by rho ux at x, y, z t plus delta t minus ux at x, y, z t. This is the momentum per unit volume, and therefore, I have to multiply this by the volume. Okay. So, the rate of change of momentum, change in momentum per unit time multiplied by the volume. This is equal to the sum of forces. Now, what are the forces that are acting on the fluid? Let us go back to the configuration. Okay. First thing, we are in a steady state configuration, so there is no time variation. Okay. And secondly, the flow is fully developed. That means that the velocity profile is the same at each and every cross section within the flow. The velocity profile does not change. Therefore, ux is independent of x, it depends only upon z. Since we have assumed that the plate is infinite in the perpendicular direction, in the y direction, there is no variation in y either. Okay. This is different from the flow in a pipe, which we will see a little later. In a pipe, it is cylindrical, and therefore, there is a variation from the center of the pipe towards the wall. Okay. In this case, the variation is only in the x direction and not in the z direction. Okay. So, if I take this differential volume here, okay, if I take this differential volume delta x, delta y, delta z, the shear stress is acting in the x direction. So, tau x z, which is equal to mu times dux by dz, is equal to force in x direction at surface with normal. In z direction. This is the force per area. Okay. acting at a surface whose unit normal is in the z direction. At the upper surface, the unit normal is in the plus z direction. Therefore, the force exerting here is tau x z. I had explained to you earlier that when you reverse the direction of the unit normal, the direction of the force also reverses. So, at the bottom surface, unit normal is in the minus z direction. Therefore, the force is minus tau x z. Okay. So, I have the shear stresses acting on the top and the bottom surfaces. Okay. So, the force exerted due to the shear stresses is going to be equal to tau x z at the top surface into the area. The area of the top surface is delta x times delta y. Okay. Delta x, delta y. Okay. At the bottom surface, the shear stress is minus tau x z. Okay. So, I will get minus tau x z at z, delta x, delta y. Okay, so, that is the force acting on the top and the bottom surfaces. However, I told you that there is a pressure gradient along the pipe as well. Okay. The pressure at each location is not the same. Pressure is higher on the left hand side, it is lower on the right hand side, and that is what is driving the flow through the tube. Okay. So, in addition, there are also pressure forces acting on these differential volumes. Okay. There are pressure forces acting on every surface. On all 6 surfaces of this differential volume, you will have pressure forces. However, for the top and bottom, there is no difference in pressure because I have not imposed a pressure gradient there. For the front and back, there is no difference in pressure because there is no pressure gradient. However, along the pipe, along the x direction, there is a pressure gradient. Therefore, the pressure at x is different from the pressure at x plus delta x. Okay. So, therefore, for this differential volume, I also have pressure forces acting. Okay. There is a pressure acting at x, okay, at the surface at x, there is a pressure acting that is acting in the plus x direction. Okay. Pressure always acts inward to the differential volume that I am considering. It is a compressive force, it acts inward. So, the pressure acting inward at x, which is in the plus x direction, there is a pressure acting inward at x plus delta x, okay, which is acting in the minus x direction. Okay. So, these two pressure forces also enter into the momentum balance equation. Okay. So, the pressure force at x is in the plus x direction, P at x, okay, times the surface area, which is delta y delta z, minus P at x plus delta x delta y into delta z. Okay. So, in addition to the shear stresses, whenever I have flow in a pipe or a channel, there are also pressure forces acting, and these pressure forces are what are driving the flow, okay, in this case. Okay. So, to get the balance equations, I once again divide by delta x, delta y, delta z, okay. And then I will get the differential equation rho times u x at t plus delta t minus u x at t by delta t is equal to p at x minus p at x plus delta x divided by delta x plus the shear stress tau x z at z plus delta z minus tau x z at z by delta z. So, that is now my momentum balance equation, and taking the limit delta x, delta y, delta z and delta t going to 0, the balance equation becomes rho times dux by dt is equal to, the second term here is p at x plus delta x minus p at x. Okay. So, this is equal to minus dp by dx, okay, and the last term is tau x z at z plus delta z minus tau x z at z, which is partial tau x z by partial z. So, that is my momentum balance equation, rho times dux by dt is equal to minus dp by dx. This is the additional term that comes in due to the pressure gradient. Okay, this is the additional term that comes in due to the pressure gradient. Previously, we had a body force term. In this case, there is a pressure gradient because the applied pressure on the two ends of the tube are different. Okay. So, and then I can use Newton's law for viscosity, tau xz is equal to mu times dux by dz, okay, to get rho dux by dt is equal to minus dp by dx plus mu d square ux by dz square. So, this is the balance equation, okay, and it contains this pressure gradient, which is an imposed pressure gradient. Okay, it is an imposed pressure gradient which is a constant along the length of the tube, and this is what is driving the flow. Okay. Note that the effect of the pressure gradient is remarkably similar to the effect of a body force. Okay. If we go back to the equation for the flow down a plane, okay, I had a similar equation, dux by dt is equal to the kinematic viscosity times d square ux by dz square plus an additional term, which is g times sin theta. In the case of a pressure driven flow, I get a term that is exactly similar to this, okay, except that it is a pressure gradient and not a body force. So, the effect of a pressure difference across the tube is similar to the effect of a body force acting on each element of the fluid. Okay. I could also write this in terms of the kinematic viscosity, dux by dt is equal to minus 1 over rho dp by dx plus the kinematic viscosity d square ux by dz square. Okay. And at steady state, okay, at steady state, dux by dt is equal to 0, and therefore, my equation just becomes minus 1 over rho dp by dx plus nu d square ux by dz square is equal to 0. Okay. Okay, so, this is the momentum balance equation, and I had two boundaries for the channel. Okay. This is at z is equal to 0, z is equal to h, and the center line of the channel was at z is equal to h by 2. Okay. So, my boundary conditions require that the velocity is equal to the wall velocity at the two surfaces. Okay. At the two surfaces, at ux is equal to 0, at z is equal to 0, ux is equal to 0, at z is equal to h. So, those are the boundary conditions that I have to solve this equation subject to. Okay. Note that once again, this is an inhomogeneous equation. Okay, it contains an inhomogeneous term here. Okay. So, there is no forcing at the walls. The velocity at both the boundaries are identically equal to 0. So, both the boundary conditions are both homogeneous. However, there is a steady forcing within the equation itself due to the pressure gradient that is applied across the length of the tube. Okay. Scaling. Obviously, z star is equal to z by h. Okay. How about the velocity ux? Once again, the velocity ux has to come from the conservation equation itself. Okay. Because if I write down minus 1 by rho dp by dx plus nu by h square d square ux by dz star square is equal to 0. Okay. And then I can divide throughout by this term here, okay, and set it equal to 1. Okay. So, therefore, I will get minus 1 plus minus 1 plus u, I write this as a total viscosity, mu by h square into dp by dx whole inverse d square ux by dz star square is equal to 0. Okay. Therefore, I can define a non-dimensional velocity ux star is equal to mu ux by h square into dp by dx whole inverse. Okay. So, that is my definition of a non-dimensional velocity in terms of the pressure gradient. As I said, there is a constant pressure gradient along the entire length of the tube. Okay. So, therefore, the velocity has to be scaled by that pressure gradient, okay, to get a non-dimensional velocity. So, this gives us the scaling for the velocity. Okay. That means that the velocity will go as dp by dx times h square by mu. Okay. So, if I apply a pressure gradient, the velocity along the tube is going to go as the pressure gradient times h square divided by mu. So, this gives me a scale for the velocity. Okay. And once I put that in, the equation just becomes d square ux by dz square minus 1 is equal to 0. Okay. With boundary conditions, ux is equal to 0 at z is equal to 0 and ux is equal to 0 at z is equal to 1. Okay. This equation is easily solved. Okay. It is a second order differential equation whose solution is quite easy to get. Okay. The solution is just of the form ux is equal to z square by 2 plus c1z plus c2, where the constants c1 and c2 are to be determined from the boundary conditions at z is equal to 0 and z is equal to 1. Okay. And these C1 and C2 can be determined quite easily, and finally, I will get an expression for ux which will be equal to z square by 2 minus z by 2. Okay. So, that is the final equation for the velocity profile. It is a parabolic velocity profile within the channel. Okay. The velocity is equal to 0 at both z is equal to 0 and at z is equal to 1. Okay. So, the velocity is equal to 0 at both z is equal to 0 and z is equal to 1. At the center of the channel at z is equal to half, the derivative of the velocity is equal to 0. So, I get a parabolic profile that looks something like this in the channel. Okay. And this parabolic profile is characteristic of all pressure driven flows. We will see a little later that when we do the flow in a pipe, that you get a parabolic flow in that case as well. Okay. So, now I can express this back in terms of a dimensional velocity. Okay. To get a dimensional velocity, all I need to do is multiply it by dp by dx times h square by mu. Okay. So, my dimensional velocity will just be equal to dp by dx into h square by mu into z star squared by 2 minus z star by 2. Okay. And this is equal to minus 1 by 2 mu dp by dx into z into z minus h. Okay. So, this is the parabolic velocity profile for the flow in a channel. It is called the plane Poiseuille flow. Okay, the parabolic profile for the flow in a channel. Okay. Now, this can also be written in terms of the mean velocity. Okay. If I take, for example, the maximum velocity at the center of the channel. Okay. So, at the center of the channel z is equal to h by 2. Okay. So, ux will be equal to minus 1 over 2 mu into dp by dx, okay, into h square by 4, okay, which is equal to the velocity u at the center of the channel. So, this is the maximum velocity, okay. At the center of the channel, the maximum velocity u is equal to, is given in terms of the pressure gradient by this expression. Okay. So, I could also express the velocity ux in terms of the velocity at the center of the channel, the maximum velocity. Okay. So, ux in terms of the maximum velocity is equal to 4u into z by h minus z by h the whole square, okay, where u is equal to this expression, the maximum velocity at the center of the channel. Okay. So, that is the velocity profile under a pressure gradient, okay, for the flow in a channel. And as I said, the velocity is remarkably similar to the velocity under the application of a gravitational force. Okay. If we go back to the previous example, the velocity in this case was also parabolic. Okay, the velocity in this case was also parabolic, except that it had a derivative equal to 0 at the top surface. Okay, it had a derivative equal to 0 at the top surface. That is because we had imposed a 0 shear stress condition at the top surface. Okay. Whereas, for our flow in a channel, the velocity was equal to 0 on both sides. The solution was parabolic, except that it came back to 0 at both walls. Okay. So, that is the only difference. If instead of having a free surface at the top, if I had had a flat solid wall at the top, I would have got the exact same velocity profile, except that it would have been parabolic and come back to 0, because I required to enforce the 0 velocity condition at the top surface if the flow is in between two flat surfaces. Okay. So, instead of the gravitational force here between two flat surfaces tending to flow the fluid down the slope, I instead have a pressure difference which is tending to flow fluid down the slope. Okay. So, that is the only difference. So, pressure differences and body forces act in a very similar manner. Now, this problem of the flow in a channel, we have used it to determine what is the velocity profile in this flow. Okay. Another situation we could consider is the effect of viscous heating due to viscosity within the flow. Okay. So, in that case, because of the flow, there is a source of energy, and that tends to heat up the channel, okay. And the objective is to find what is the temperature, okay, due to this viscous heating within the channel. Okay, so let us look at that problem, which is now a problem of a source of heat, okay, within the channel. Okay. So, this is the problem of viscous heating. In the channel. Okay. So, I am given a velocity profile. Okay. This is x, this is z. Okay. I know that the velocity profile is given by this profile, and I want to know what is the temperature. Okay. So, we are maintaining, for example, in a heat exchanger problem, we maintain the temperature T is equal to T naught on both walls, and we would like to know what is the temperature within the fluid due to the viscous heating. Okay. So, that is the problem. We will not derive in detail here, but the source of energy due to viscous heating, okay, is given by the source per unit volume is equal to the shear stress times the velocity gradient. Okay, the source of heating per unit volume, energy generated per unit volume per unit time is the product of the shear stress and the strain rate. Okay. And we will assume that this formula for the shear stress and strain rate is given to us. Okay. So, we will not try to obtain it. Okay. So, with this expression for the rate of viscous heating, okay, the heat transfer equation is of the form dT by dt is equal to the thermal diffusivity d square T by dz square plus SE. Okay. With boundary conditions, T is equal to T naught at z is equal to 0 and is equal to T naught at z is equal to h. Okay. So, those are the boundary conditions. So, using these I have to solve this equation. Okay. Scaling, as usual, we can define the z coordinate as z star is equal to z by h. What is the scaling for the temperature? Okay. So, for simplicity, I will define the scaling here for the temperature as T star is equal to T minus T naught divided by T naught, the fractional rise in temperature due to the viscous heating. Okay. We will work with this, and then we will see that we will get a dimensionless number which gives you the rate of viscous heating as compared to the temperature rise. Okay. So, inserting this into this equation, okay, and assuming steady state. Okay. So, at steady state, dt by dt is equal to 0. Okay. So, this is a steady configuration and there is viscous heating. So, my differential equation becomes alpha d square T by dz square plus SE is equal to 0. Okay. Now, what is the source? Okay. I told you that SE was equal to tau xy times, I should be careful here, tau xz times du x by dz. Okay. But from Newton's law of viscosity, tau xz is just equal to mu times du x by dz. Right. So, I can write this as mu times du x by dz the whole square. Okay. So, that is my expression for the viscous heating per unit volume per unit time in the energy balance equation. Okay. Sure. And this becomes K. Okay, the thermal conductivity. Okay. Now, we know that ux is equal to 4u into z by h minus z by h the whole square, okay, which means that dux by dz is equal to 16 u square by h square by 16 u by h. One minus 2 z by h. Therefore, SE will be equal to, I should write this as 4. (16u square by h square into 1 minus 2z by h the whole square, okay, which is equal to 16u square by h square into 1 minus 2z star whole square. Okay, so that is the final expression for the rate of production of energy. Okay. And if I put that into my conservation equation, I have k times d square t by dz square plus 16u square by h square into 1 minus 2z star the whole square is equal to 0. So, this is my energy conservation equation in the presence of viscous heating within the flow. Scalings, I had defined z star is equal to z by h and t star is equal to t minus t naught by t naught. Okay. So, that I have t star is equal to 0 at both boundaries. Okay. With that scaling, you can write this as k t naught by h square d square t star by dz star square plus 16 u square by h square to 1 minus 2 16 mu. Is equal to 0. Okay. And I can divide throughout by this first factor, okay, in order to get an equation of the form d square t by dz square plus a dimensionless number, okay, a dimensionless number times 1 minus 2 z star square is equal to 0. This number is usually defined with a prefactor, so I will just leave that definition of the prefactor there. I will leave that definition of the prefactor there. Okay. There's a mistake here. Okay, so I will define it with the prefactor, where this thing, okay, this dimensionless number is given by mu u square by k t naught. Okay. It's sometimes called the Brinkman number. Okay. I'll just leave it as a dimensionless number here. Okay. So, this basically gives me the ratio of viscous heating to the temperature rise due to a temperature difference proportional to T naught. Okay. The mu u square is the rate of energy generation per unit volume, okay, due to viscous heating, okay, mu u square by h square, and k T naught by h square is the rate of change of energy within a volume if there were temperature gradient of magnitude T naught over a distance h. Okay. So, that is the physical significance of this dimensionless number. This equation can be easily solved to get the temperature profile. Okay, the final solution for this equation is T star will be equal to this Brinkman number into 8z 1 minus z star 1 minus 2 z star plus 2 z star square by 3. Okay, that is the final solution for the temperature increase. Okay. And if you actually plot out this temperature profile, okay, this temperature across the channel, it has to come to 0 at the two walls. Okay. At the center of the channel itself, it is very flat. Okay. The temperature actually looks something like this. Okay. So, this is the temperature as a function of the height, okay, the function of z. This shows you the temperature profile. It is much flatter than the parabolic profile for the velocity itself. The reason is because at the center of the channel, the shear stress goes to 0. The slope of the velocity is equal to 0 at the center of the channel. Therefore, dux by dz is equal to 0 at the center of the channel. Therefore, at the center of the channel, there is no viscous heating. Okay, and because of that, you do not have any variations in temperature right at the center. At the walls, of course, the shear stress is non-zero. In fact, the shear stress, the slope of the velocity profile, is largest at the walls. Because of that, the heating is also largest at the walls, and therefore, you have the largest temperature difference at the walls. Okay. Now, one can calculate the heat flux. Okay. Qz is equal to minus k times dt by dz. Okay. This is true of any location. Okay. Qz is equal to minus k times dt by dz. Okay. I can write this in terms of the dimensionless variables t star and z star as minus k t naught by h dt star by dz star. Okay. And if I put in my expression for the heat for the temperature profile here, if I put in this expression for the temperature profile, okay, what you get is that Qz is equal to eight k T naught by 3 h into 1 minus 2 z star, the whole cubed, okay, into the Brinkman number. Alternatively, I can write it in terms of the viscosity and the velocity of the fluid. Just from my definition of the Brinkman number, mu u by k T naught as 8 mu u square by 3 h into 1 minus 2 z, the whole square, the whole cubed, I am sorry. Clearly, this is a maximum at z is equal to 0 and at z is equal to z star is equal to 1. At the top and the bottom surfaces where z star is equal to 0 and at the top surface where z star is equal to 1, this heat flux is a maximum. Okay. It is going outwards. Okay. That means that it goes downwards at z star is equal to 0. And therefore, should go upwards at z star is equal to plus 1. At the center itself, the flux is equal to 0. At the center, z star is equal to half, and therefore, the flux is equal to 0, okay, at the center itself. And that was because the velocity gradient is 0 at the center, as I had explained to you a little earlier. So, the maximum heat flux due to viscous heating Qz is equal to 8 mu u square by 3 h. Okay. That is the maximum heat flux due to viscous heating. Okay. And this heat flux actually has relevance in the context of the heat exchanger problem that we had solved in the second or the third lecture. Okay. If you recall, we had solved this problem using dimensional analysis. In this problem, when we did the dimensional analysis, we had separated out the quantities into thermal and mechanical quantities. Okay. We had said that there is no interconversion of energy from thermal to mechanical energy. Okay. Strictly speaking, I had 1, 2, 3, 4, 5, 6, 7, 8, 9 variables and 4 dimensions. So, I should have been able to get 5 dimensionless groups in this problem. Okay. However, I said if there is no interconversion of energy from thermal to mechanical, then I can consider heat energy to be separate from mechanical energy. Okay. And if heat energy is considered to be separate from mechanical energy, then I have 5 dimensions, because heat energy is a separate dimension. And I have 5 dimensions, 9 dimensional groups. That means that I have only 4 dimensionless groups, which ultimately we identified as the Nusselt number, the Reynolds number, the Prandtl number, and the ratio d by L. Okay. So, the assumption here is that heat and mechanical energy are separate. There is no interconversion, and therefore, I can write a balance for the heat energy alone. Okay. I do not need to consider the fact that mechanical energy can be interconverted into heat energy. Okay. In the problem that we just solved, in the problem that we had just solved, I told you what is the heat energy generated due to viscous heating. This heat energy generated due to viscous heating represents an interconversion of energy between mechanical energy and heat energy. Okay. Therefore, I can consider heat energy to be separate only if this flux due to viscous heating is small compared to the flux due to temperature difference. Across the wall, across the tube wall. Okay. So, it is only under these conditions that I can consider the heat energy and the mechanical energy to be two different things and write different balances for these. Okay. What is the flux due to the temperature difference? Qz is equal to K delta T by delta Z, where delta Z is the thickness of the tube. Okay. Therefore, I require that mu u square by 3 h is small compared to K delta D by delta Z. Okay. In order to be able to neglect the viscous heating in comparison to the actual energy transfer across the tube wall. The energy transfer across the tube wall just depends upon the wall thickness. Okay. So, this is just equal to the thickness of the wall. Okay. Whereas, the viscous heating energy depends upon the thickness of the entire tube. Okay. The thickness of the entire tube is usually small compared to the wall thickness. Okay. And therefore, my requirement is that delta T has to be large compared to mu u square h w by h times k. Okay. So, only if this temperature difference is large compared to the temperature that is generated due to viscous heating, will I be able to neglect viscous heating in comparison to the heat exchange due to the temperature difference across the tube. Okay. And it is only in that case that the assumption that the heat energy is separate from mechanical energy is a valid one. Okay. So, that depends upon, as I said, on this Brinkman number, okay, this number that I have. If I assume that delta T is of the same magnitude as T w, then the Brinkman number gives me the ratio of viscous heating and the heat generated due to temperature differences, if delta T is of the same magnitude as T w. Okay. And if the Brinkman number is small, then I can neglect, okay, the heating due to viscous friction in comparison to the heating due to the heat flux due to temperature difference across the tube. Okay. So, we solved problems where there are sources and sinks for momentum transfer. We solved two problems. One is where there is a body force which tends to force the fluid, and the other is where there is a pressure difference across the ends which results in a pressure gradient along the tube. Okay. I showed you that the effect of the pressure gradient is effectively equivalent to the pressure due to a body force acting on the fluid. And then we solved a problem here of the temperature, the heat generated due to the viscous flow within the channel. Okay. In a similar manner, one can write down equations for the concentration field as well. Okay. We had seen the concentration equation a little earlier. Okay. dC by dz is equal to d square c by dz square plus any source or sink. Okay. In the concentration equation, the source of mass or the sink of mass is due to chemical reaction. Okay. And therefore, the source or sink will depend upon the reaction rate and the concentration. Okay. The source and sink are usually of the form source is equal to either Kca minus Kc if C is concentration of a reactant, or will be equal to plus K times C if C is the concentration of a product. Okay. So, this is for first order reactions. Okay. If the reaction is second order, then it will go as C square. Okay. If it is an nth order reaction, it will go as C power n. Okay. The equation continues to be linear only if the reaction is first order. Okay. If the reaction is second order, the equation is no longer a linear equation. Okay. So, you have to have some special ways of solving the equation if it is a higher order reaction. Okay. However, if the reaction is first order, there is an easy way to solve it. Okay. The reaction at steady state d square c by dz square minus k c is equal to 0. Okay. And from the reaction rate and the diffusion constant, you end up getting a length scale out. Okay. So, if I divide throughout by the diffusion constant, I get d square c by dz square is minus k by d c is equal to 0. Okay. If I define c star is equal to c by c naught, okay, I get a length scale out of here. Okay. Z star is equal to z times k by d power half. This is non-dimensional because k is a reaction rate, it has dimensions of time inverse, and d is a diffusion coefficient, it has dimensions of length square per unit time. So, this z star is a dimensionless number. Okay. So, this dimensionless number comes out of the analysis, and my equation becomes partial square c star by partial z star square minus c star is equal to 0. Okay. So, this has exponentially increasing and decreasing solutions. Okay. This equation has exponential solutions. Okay. So, this length scale is effectively a penetration depth. The depth to which a perturbation to the concentration at a given surface will penetrate within the flow. Okay. So, if this penetration depth is small compared to the macroscopic length scale, then the effect of any concentration field at the bottom will be felt only to within a finite depth within the fluid. Okay. So, this thing acts as a penetration depth within the flow. Important point to note is that in this case where we have a reaction and a diffusion system simultaneously, the fact that you have reaction as well and that reaction rate depends upon concentration. In the previous case for viscous heating, the heating rate did not depend upon temperature. So, it was independent of temperature. In this case, reaction rates usually depend upon concentration of reactants or products. Okay. So, if it depends upon concentration, you get out a penetration depth, okay, from this exercise. Okay. So, so there is an additional length scale that comes into play apart from the length in the from the width of the channel. In the case of flow in a channel, that was the only length scale in the problem. In this case, there is an additional length scale, which is the which is related to the ratio of the reaction rate and the diffusion coefficient. Physically, the system, the concentration diffuses from the surface, but it is also getting consumed within the flow, and therefore, because of that it will penetrate only to a finite depth within the fluid. Okay. So, that is a characteristic of diffusion problems in diffusion reaction problems in mass transport. Okay. There is an additional complication in mass transport problems, and that is that one has to account for the center of mass velocity. Okay. The flux, if the concentration of the mass being transported is small, then its transport does not result in a velocity of the center of mass, but if it is finite, there is a center of mass velocity. We will look briefly at that center of mass velocity in the beginning of the next lecture, and then we will go on to analyzing problems in cylindrical coordinates. So, this completes sources and sinks within the flow for unidirectional transport in Cartesian coordinates. The next is to go to cylindrical coordinates. Before that, we will just briefly look at mass transfer problems. So, we will see you in the next lecture.